Alright, so in this series of videos, we're going to be talking about how to find the surface area and volume of triangular pyramids that have an equilateral triangle for its base. So starting with our vocab up at the top of the page, a triangular pyramid is a pyramid with a triangular base. In the problems you'll be completing, these bases will all be equilateral triangles as is shown at the right. The height of the pyramid is the distance between the vertex and the center of the triangular base. The slant height of the pyramid is the altitude of any other face. The slant height divides the base edge into two congruent segments. So this is very similar to what we talked about with square pyramids. We have the height that comes from the vertex down to the center of the base. That's what we refer to as h. The slant height is coming from the vertex down the triangular face to the midpoint of a base edge, and we refer to that slant height as L. And then the apothem completes that right triangle from the center of the base out to the midpoint of the side. The apothem, you might recall, is indicated by a lowercase a. Now, as we've stated previously, this right triangle means that the Pythagorean theorem could be involved. A squared plus h squared equals L squared. What we're going to be doing in this video is talking a little bit about the apothem specifically, and then in the next video we'll talk about how to actually find the surface area and volume for the pyramid itself. So let's look at our example or our diagram that we have here and the example given. The triangle given below is an equilateral triangle with its apothem shown. Assume each side of the triangle is 20 units long. Find the length of the apothem. So we have an equilateral triangle, each side being 20 units long. We already know that the apothem comes from the center of the polygon to the midpoint of a side, which means this 20 unit long side is now cut into two portions, each 10 units long. Now, in order to find the length of the apothem, we need to kind of revisit some special right triangles. And this is not the first time in this chapter that we've had to do that. With this equilateral triangle, we know that it has 360-degree angles initially. Specifically, though, I want to take this third angle, that third 60-degree angle, and I'm going to look at its angle bisector for a moment. Now, if I bisect that angle, this angle bisector is going to pass through the center of that polygon, which means it's going to intersect that point where A's end point is located. And it's going to cut this angle into two 30-degree angles. We know also that the apothem is perpendicular to the side, which means this triangle here formed by this 30-degree angle A and that side length 10, we know that that is now a 30, 60, 90 triangle. Now you may recall with 30, 60, 90 triangles, let's kind of sketch one over here for a minute. The side opposite the 30-degree angle is what we referred to as the short leg. It is the shortest side in the triangle, and we represented it with a length of x. Or there were two properties that existed for the lengths of the other two sides. If we took the short leg times 2, it gave us the length of the hypotenuse. And if we took the short leg times the square root of 3, it gave us the length of the longer leg. Now comparing that to the triangle that we have here, our x value is an a, and the x square root 3 value is a 10. Which means in this case, if I'm trying to find the length of the apothem, then I'm going to use the same rule we applied here. Take the short leg times the square root of 3. So in this case, the short leg A times the square root of 3 equals the length of this longer leg 10. And from that, we can find the length of A. So we divide both sides by the square root of 3 and rationalize on the right side, multiplying both the numerator and denominator by that square root. So on the left side, we're left with a. On the right side, in the numerator, we have 10 square root 3, and in the denominator, a whole number 3. You may recall that when this 10, if it were divisible by that whole number 3, then I'd go ahead and reduce it. For example, if that were a 6 square root 3 over 3, then I'd reduce and make it 2 square root 3. Here, 10 is not divisible by 3 evenly, so it's best to leave it in that form. So to find the length of the apothem, keep in mind that your special right triangle exists. You will always, in these exercises, be given the length of a side. So the length of the apothem times the square root of 3 is going to be equal to, in this case, half of the side length, because we're only looking at half of that side. In the next video, we're going to look at how these surface area and volume formulas that we see here at the bottom of the screen, how those are going to be used in the actual pyramid itself.